So to start this off, what we're going to be talking about here is choosing the appropriate reagent for a given reaction. Okay, so we're going to start this off by talking about this guy, which is the acetate ion. So this guy over here is acetate, right? And in this question, what we want to do is we want to protonate acetate. We want to put a proton on acetate, forming its conjugate acid. And the question that we're asking is water a strong enough of an acid to do this? So can water protonate this negative charge in oxygen, forming acetic acid and then its conjugate base, okay? So if we draw that out, we have water, and we'll go ahead and draw out the structure of water, right? We're asking whether or not this is a strong enough acid. So in this acid-base reaction, we've got our base as acetate, we've got water as our acid. If I wanted to draw the mechanism, where would I start my little arrow, my curved arrow notation? I'd start it specifically at the electrons on the base, right? So the lone pair is going to go out. It's going to get a proton, right? This bond is going to break, leaving behind that pair of electrons on our conjugate base, right? And we're going to form, as our products, our acetic acid, our protonated acetate ion, plus the conjugate base of water, which is just the hydroxide ion. So the question that we're asking right now is if this is a strong enough acid to undergo this reaction, or more importantly, for this reaction, will products be favored at equilibrium? If products are favored, then this is a strong enough acid to protonate this, right? Because it does it, it produces the products, we're favored at equilibrium, okay? So, same type of concept. How do you think I'm going to figure that out without pKa values or anything like that? If I want to figure out which side of equilibrium is favored, who should I be comparing? My bases, right? So I need to look at the bases for both. I've got one conjugate base over here, hydroxide. Who am I going to compare that stability to? Who is the base on the other side? Acetate, right? And so we're going to try to figure out between these guys who is more stable, okay? How do I do that? What is my first letter in my little acronym?
It's A for atom.
A for atom, right? So we've got, first off, atom. So number one, we've got atom. Where does the negative charge lie on both of these guys? Oxygen over here. So we've got the negative charge on oxygen for acetate. Where is the negative charge for the conjugate base hydroxide?
The same place.
It's also on oxygen, right? So that doesn't help us. They're both oxygen. So we can't determine via atom. Who comes next after atom? Resonance, right? So now the question is, do either of these guys have resonance structures? So for hydroxide, which is this guy over here, are there any other ways that we can draw this?
No.
No, right? We have lone pairs, but we don't have any type of double bond situation. There's no charge separation, so there are no resonance structures over here. So no. What about acetate? Is there any other way to draw this?
Yes.
So we think back to our patterns. We've got a lone pair of electrons in what position to the double bond?
Adjacent to the double.
What is this called?
Allylic.
Allylic, right? So we have a lone pair of electrons in an allylic position. So one of our patterns is a lone pair going to form a double bond here, breaking this double bond, pushing those electrons up on the other oxygen. And so the other way we could draw this looks like this. Right, so there are two structures that go in for acetate as opposed to just the one structure with respect to hydroxide. So then because of that, who's more stable? We don't even have to think about the next one. We've already found a point of difference. We've got resonance for acetate. We have no resonance for hydroxide. So who is the more stable, acetate or hydroxide?
Acetate.
This guy's hydroxide. We're comparing this guy, we'll write that above.
The hydroxide is more stable.
Hold on. Hydroxide versus acetate, right? Again, we're trying to figure out who is more stable using a Rio. The first thing that we're looking at was atom, oxygen. Oxygen, that couldn't tell us anything. But the second thing, this guy, hydroxide, didn't have any resonance structures, whereas acetate did, right? And remember that resonance is stabilizing. It's overall like a stabilizing force. And so because of that, because this guy does have resonance, acetate is the more stable conjugate base, or base, we'll just say. And therefore, again, equilibrium is always going to favor production of the more stable base. Which side is going to be favored at equilibrium?
Yeah.
Reactants or products? Reactants, because again, this guy is more stable. We're always going to favor formation of this. So this whole question of, is water capable of doing this reaction? When we look at this reaction overall, reactants are going to be favored at equilibrium, which still has this in a deprotonated form. So is water strong enough of an acid to protonate acetate?
Yes.
If it was, this would be our favored side of equilibrium, which it is not. The more stable conjugate base is acetate.
I see.
This is our favorite side of equilibrium. So the question, is water capable of doing this reaction and producing these products, is no. Because again, this is more stable. This is the side that's going to actually be favored at equilibrium. Okay, so for this guy, determine whether water is suitable. It is no, because acetate is a more stable conjugate base comparatively to hydroxide. The arrow. So the answer would be yes if products were favored. But because reactants are favored, the answer to this question is no. This reaction won't occur. Water is not strong enough of an acid to do this reaction. Yes?
Would I care about the arrows? So if this is my equation, my biggest arrow would face where?
So for this one, I just drew the arrow in to make sure that we saw the difference, but now this guy would be what the arrow would look like.
Because it's more favored.
Yeah.
More stable.
Because reactants are favored because this is more stable.
If you drew an arrow for the Alkane.
So this is one of the various types of questions that you could answer utilizing this type of idea. Okay, again, you're determining who's favored at equilibrium, reactants or products, right? When they ask about a reagent being capable enough to do a reaction, you should write out the full reaction and then compare the stability of the two bases, figure out who's more stable. Equilibrium will always favor that side. If they're saying, are products favored, is this reaction capable of happening, then you'd be good. But if you find out, oh, reactants are actually favored, this reaction won't occur, then no. Whatever that reagent is, it's not capable of doing the thing that it's being asked to do. Okay, so I have a couple of these to go ahead and practice with respect to choosing a suitable reagent, okay? So I'm going to add to this guy. So I have a couple where I have a molecule, so let's say this guy, and I want to know, can I use water to protonate this? That's the question I'm asking, right? Just like I said, I had acetate. I want to know if I can use water to protonate acetate. Right now I'm saying, I've got this guy. Can I use water to protonate that? Okay, so let's try to answer that one. And then I want to know on this one, I've got this thing. Can I use this NH2 minus ion? This is called the amide ion. Can I use that to deprotonate this? Okay, so we'll focus on these two, ignore this one down at the bottom, and then we'll go over it together, okay? So I'm gonna. The next thing we're going to talk about is something called the leveling effect. And so in general chemistry, the majority of our acid-base reactions took place in what solvent, specifically? Pretty much all the reactions we talk about in general chemistry take place in what? Water, right? So the majority of things that we deal with in general chemistry always took place in water. There's an issue with that as we move into organic chemistry, okay? So for example, I just introduced you guys to the amide ion, right? This NH2 with the minus, right? Again, I've also said that this is a very, very, very strong base, okay? So let's say that we did have something like acetylene, right, with this triple bond carbon to hydrogen. Sodium amide, or amide, is a strong enough base to deprotonate this, right? And let's say we wanted that reaction to occur for whatever reason. We wanted to use amide, we wanted to deprotonate this, okay? If I put that reaction in water, there's a big issue with respect to that reaction actually occurring at all, right? So for example, if I put amide in water, every time it finds a water molecule, it's going to act as a base, right? It's going to go out, take a proton, leaving behind the electrons that are in this bond, producing hydroxide as a product, okay? Looking at this reaction, which side of equilibrium is going to be favored? The side with hydroxide as a base or the side with the amide as a base? Who's a more stable? Products, right? So hydroxide, because the negative charge is on oxygen, is going to be more stable, so the products are going to be favored at equilibrium. Now, you put amide into water, what is the strongest base that you get? Because amide's a great strong base. We'd love to use it in this reaction, right? The minute you put it into a solvent like water, though, what is the strongest base that you get? It's just hydroxide, right? So the idea behind this is something called the leveling effect, right? If we were to try to do this reaction in a solvent like water, the strongest base that we could possibly get out of it would just be hydroxide. Hydroxide is not capable of deprotonating this. Amide is, right? And so when you're trying to utilize a very strong base like sodium amide, you can't use a solvent like water because it will react with water, forming a weaker base overall. So for a reaction like this, we would instead like to utilize a nice solvent like liquid ammonia so that it won't react with whatever the solvent is, and it will actually keep that strong sodium amide base that we want overall, okay? So you just have to be aware of this. A lot of times that's why water isn't utilized in a lot of these organic reactions, is because it will react with whatever we're trying to use. So in this example was the base, and we'll put a weaker base overall. So because of that, we will usually utilize bases like hexane and THF. This is tetrahydrofuran. These guys are super, super, super stable, right? They will dissolve whatever you need to dissolve, and they will not react with it overall because they're going to have overall a much, much stronger conjugate base than in H2, okay? So when you're choosing a solvent, you always want a solvent that's going to have a stronger conjugate base than the base that you're actually trying to use, okay? Okay, so same exact thing with acids, right? Whenever we talked about something like sulfuric acid, so something like H2SO4, we always said, oh, this is a strong acid, right? We put it in water, it protonates water, forming the hydronium ion, okay? This same exact leveling effect occurs, right? Sulfuric acid is a much stronger acid than hydronium, but when you put sulfuric acid in water, the strongest acid that you're left with is hydronium, right? So again, if you want a stronger acid than hydronium, you need to utilize a solvent that isn't going to actually react with your acid, okay? Okay. So that's just a little bit of a thing to note. With respect to picking a solvent, there's a couple other things that we'll talk about, and then we'll move on to chapter 4, okay? Okay, so in comparing our little conjugate bases, right, we've utilized our nice little AREO acronym. That's really, really, really great, but it doesn't always explain all of the things that we see with respect to the stability of these bases, right? So let's compare, let's say, something like terbutanol as an acid to ethanol, okay? Now, if I wanted to compare these guys and figure out who is the stronger acid without looking at the pKa's, I would deprotonate both, so I'd take a proton off of both, and I would look at their conjugate bases, right? So for ethanol, we would be left with this guy with the negative charges on oxygen, and then for terbutanol, we would be left with this guy where the negative charge is on oxygen, okay? Now, again, the more stable the conjugate base, the stronger the acid. If I'm comparing these conjugate bases, where does the negative charge lie at on both of them? Oxygen, right? So no point of difference there. Do either of these guys have resonance structures? No, right? What is AREO? What is I? Induction. Are there any type of electronegative bonds or anything in either of these molecules? No. And then what type of orbitals do they both or do the lone pairs both lie in? sp3 and sp3, right? So using AREO right now, we can't actually determine who is the more stable conjugate base, therefore who is the strongest acid, okay? But there is a difference, right? Who is the strongest acid here?
I want to say more ions.
Just looking at the pKa's, who's the stronger acid?
Ethanol.
Ethanol, right? So this guy is stronger, meaning that for whatever reason, this is the more stable base, right? And so now this last little bit comes into what the solvent around these conjugate bases is actually doing, okay? So let's compare the structure of ethanol to this tert butoxide, this guy, right? So with this guy, we've got a carbon here, and we've got a carbon to a bunch of tiny little hydrogens, and we've got a bunch of little hydrogens here. What about over here? What are these groups instead? These are all CH3 groups, right? So carbon with a bunch of other hydrogens, okay? Who do you think is going to take up more space?
Take up turbic.
Right, tert butoxide, right? So this guy is what we would call very bulky, right? So this deals with something called steric hindrance. So steric hindrance is all of these electrons in these bonds, right? They kind of produce this negative charge, big thing overall. Because of that, our little solvent ions aren't capable of getting in and actually stabilizing that negative charge, right? So because this guy is big, it's bulky, the solvent ions, which help stabilize this negative charge as well, aren't capable of getting in and stabilizing it as well. Ethoxide, on the other hand, is nice and small, just has these tiny little hydrogens, isn't sterically hindered, so solvent's able to get in quite well and actually help stabilize that negative charge, okay? So the last little thing that we talk about is the solvent effects. Because solvent's better able to get in and stabilize a negative charge that forms on ethoxide, this ends up being more stable, and so ethanol ends up being the stronger acid. So that last little thing that you have to consider is, can solvent get in and help stabilize this as well? For tert butoxide, it can't because it's big, it's bulky, sterically hindered. For ethoxide, it can because it's not. So we call this bulky a lot. Okay, so that's kind of our last little thing with respect to acids and bases. So solvation effects and the ability to stabilize these conjugates. Okay, so I didn't go over these last few slides in class, but I'm going to go ahead and go over them in the recording. So this last little bit is kind of just, I don't know, covering all of our bases, I guess, if you will, with bases. So we just talked, I think, about that amide ion, right, that NH2 that has the two lone pairs and the formal charge on nitrogen, right? And so this is our nice strong base. It's a very strong base, right? It's strong enough to deprotonate things like acetylene, right? So that's kind of where we made this argument, who's the stronger base. But again, with respect to amide, this actually has a formal charge, right? And so this has an actual total negative charge. This is an anion, right? And so even though we're saying, oh, we're going to use this amide ion, this always has to be paired with something to neutralize that negative charge, right? So we actually put this into a reaction, we put this into solution, it's going to be paired usually with some sort of positively charged cation. And a lot of times, especially with amide ion, this ends up being just sodium +1, right? So when we put this into solution, we'll put it in as sodium amide, right? This entire compound, this is our neutral ionic compound. But in reality, that sodium really doesn't do anything, right? It's just acting as a spectator ion. So this is just, it's there, it's floating around. It doesn't really actually participate in any type of reaction. The real reaction that is taking place is the amide, which is our base, is deprotonating water, forming hydroxide and ammonia, okay? So note that we sometimes won't mention it, sometimes we will, not to be confused by it. If you do have something that has a negative charge, it always has to come along with some sort of positively charged species, and that's usually going to be a sodium or potassium or something like that, right? Some sort of counter ion, some sort of spectator ion that doesn't actually do anything in the reaction. This, and then I talk about Lewis acids and bases. We're going to cover this a little bit later, right? So there is another definition with respect to acid-base theory. We're going to come back to it when we start talking about actual reactions and mechanisms, okay? And so we'll put that on the backboard. Okay, so then finally, we're going to get into Lewis acids and bases. So with respect to Bronsted-Lowry acid-base theory, right? In Bronsted-Lowry theory, a Bronsted-Lowry acid, so a Bl acid, was a proton donor, right? It's an acid because it donates a proton, whereas a Bronsted-Lowry base was a proton acceptor. So Bronsted-Lowry acid-base theory focuses on the proton, what happens to protons, right? What we're going to find, though, is that a lot of reactions that we deal with, a lot of acid-base reactions, don't actually involve a proton at all. So they can't really be defined under Bronsted-Lowry theory because it has to have a proton to be a Bronsted-Lowry acid or base. So because of that, we have another theory, and it's called Lewis acids and bases. And Lewis theory and Lewis acids and bases are really what we're going to utilize a lot as we move into organic chemistry. And it makes a lot more sense with respect to how we depict our curved arrows, right? And how we have our base go get protons. That makes a lot more sense when we utilize Lewis acid-base theory as opposed to Bronsted-Lowry acid-base theory, okay? So for example, we have a reaction, we have water reacting with HCl, forming H3O plus and Cl minus. In this reaction, we have HCl acting as our Bronsted-Lowry acid because it donates a proton to water, forming H3O plus. We also have water acting as our Bronsted-Lowry base because it accepts a proton from water, forming H3O plus, right? So again, this focuses on the proton transfer reaction. Now, water is a Lewis base as well, right? But the definition for a base under Lewis theory is different. So instead of focusing on protons, what Lewis theory does is it focuses on electrons, right? So water's a Lewis base because Lewis bases are electron donors, right? Water's got this nice lone pair of electrons that it goes out and donates to the proton, right? And forms a new bond with, essentially, right? So a Lewis base is an electron donor, whereas a Lewis acid, which happens to be HCl in this reaction, is a Lewis acid because it's an electron acceptor, right? The acid portion of our Lewis acid accepts these electrons from water, right? Forming the various products, okay? So Bronsted-Lowry bases are Lewis bases, and Bronsted-Lowry acids are Lewis acids. It's just the definition changes, right? So to be a Lewis base, you have to be an electron donor, right? And to be a Lewis acid, you have to be an electron acceptor. Okay, so what's so great, I guess, about Lewis acid-base theory is that, again, it helps explain acid-base reactions that don't actually involve the transfer of protons, whereas Bronsted-Lowry theory can't do that, right? So for example, if we have a problem here where we have water reacting with this BF3 molecule, forming this complex over here, there is no transfer of proton, right? So this does not fall under the umbrella of Bronsted-Lowry acid-base theory. It does fall under the umbrella, though, of Lewis acid-base theory, because right now we have water that has these lone pairs of electrons. They are donating their electrons to this boron, right? So here, water is acting as a Lewis base. It's acting as an electron donor. And this BF3 molecule is acting as a Lewis acid. It is acting as an electron acceptor. So again, this type of reaction can't be explained by Bronsted-Lowry acid-base theory. It can be explained by Lewis acid-base theory. And so just as a note, we're going to get more into this as we move into the various reaction mechanisms that we talk about at the end. But Lewis bases always tend to be fairly electron-rich things, right? So they tend to have lots of electrons, lots of lone pairs. They can be both negatively charged, or they could just have, an electron-rich likeness to them. whereas Lewis acids tend to be very electron poor, right? So they can have a formal positive charge, or they can just be molecules that maybe are partially positively charged due to induction or something like that, okay? So Lewis bases, we also have another name for them. They're electron-rich species, meaning that they tend to have that extra electron, extra negative charge. Because of that, we tend to call these guys nucleophiles. And as a reminder, philes or philic means loving. So if you're nucleus loving, protons or positively charged molecules are in the nucleus, that means that you yourself are negatively charged, right? So Lewis bases are called nucleophiles. They love the nucleus. They love the positive charge there because they themselves are negatively charged. Whereas Lewis acids tend to be called electrophiles. So again, same basic idea. Lewis acids are positively charged. They love electrons, so they love negative charges, right? So they're wanting negative charge to come around them. They're electrophilic. Okay, so that's it for this chapter. So hopefully that makes a little bit more sense with respect to Lewis acid-base theory at the end. It is kind of, again, a very long chapter. There's a lot of information covered in it. And it's going to deal with kind of our first big organic class of molecules, which are alkanes. Okay? So I'm going to define what an alkane is, and we're going to talk about them. We're going to talk about alkanes as well as cycloalkanes. So again, we will define this as we move through. Okay, so number one, when I say alkane, do you guys already have an idea in your mind of what an alkane is? One line, something? Just single lines? That's probably pretty good to think of with respect to alkanes. So with respect to alkanes are a class of hydrocarbons, right? So when I say hydrocarbons, what does that imply overall? Just hydrogen and carbon, okay? So hydrocarbons are just molecules or compounds that contain only hydrogen and carbon. So this can be hydrogen and carbon single bonds, right? Like we see in this molecule ethane. It can also be carbon and carbon double bonds, like in acetylene, or carbon and carbon triple bonds. Like in ethylene, and then carbon-carbon triple bond is acetylene, okay? So all of these guys count as a hydrocarbon, because again, the only thing that they have in them is hydrogen and carbon. Now, what differentiates these guys from alkanes? So alkanes are also hydrocarbons, right? They only have carbon and hydrogen, but alkanes lack any type of pi bond, right? So alkanes do not have any pi bonds, meaning that they don't have what type of bond? They don't have a triple, they don't have a double, right? So all we're going to be looking at with respect to alkanes are carbon single bonds, and carbon-hydrogen single bonds, okay? This is the most basic of all of our organic molecules. Now, how do I know that I'm dealing with an alkane? It lies at the end of the word, right? So all alkanes have a suffix of A N E. Okay, so that is characteristic that you're talking about an alkane if it ends in A N E. Okay, so that is the basics of alkanes, right? So it's going to be hydrocarbons that do not have any type of pi bond. So only carbon-carbon single bonds, carbon-hydrogen single bonds. Now, the first thing that we're going to talk about in this big chapter with respect to alkanes is how to name things appropriately. Okay, so chemical nomenclature is going to be what we start with. And this is going to be kind of a big branching topic that we're going to continue to come back to throughout. So it's important that you guys get these rules down at this point in time. Okay, so just going back, kind of forming this idea of why it's important to name things appropriately. So back whenever organic chemistry was just starting off, anytime someone synthesized a new compound or isolated a new compound, they would usually name it at their own whim, right? So for example, the guy who isolated formic acid for the first time named it formic acid because he isolated it from ants, and the Latin word for ant is formica. Okay? Urea is another example, right? Urea was originally isolated from urine. That's why it has the name urea. All right, so now, ideally, this should present kind of a problem. If we're just naming things at whim, without any systematic set of rules, to know a molecule and then also know its name, what would you have to do? You'd have to memorize every molecule and every name, right? But there are a bajillion different types of molecules that you could make or that you could isolate. So there's an issue with that, okay? Also, with respect to general chemistry, because we spend a lot of time in general chemistry talking about how to name things appropriately, right? In general chemistry, how would you have named a compound like this, C4H10? What would you have given it a name of?
Core carbon.
All right, so this would be tetracarbon, and then 10 is like decahydride. So if I said, hey, I want to name the C4H10 thing, I'm going to call it tetracarbon decahydride, what's the problem with that?
It's a big name.
It's a big name. It's not. They're going to get bigger. That's not the big problem with it.
I think they get to affect line structure.
Line structure, right? Because how many different ways can we draw C4H10? Right, so we could draw it as all the carbons attached with hydrogens, right? How else can we draw this? And then we could have maybe a carbon branch down here. What are these guys called again?
Isomers.
These guys are constitutional isomers. Right, so how do we specify isomers? How do we specify that this is tetracarbon, decachloride, or decahydride versus this guy? How do we specify that? Because again, long term we want to name and we want to be able to know what that structure is going to be. Okay, so these are my two big arguments of why nomenclature and why a very nice systematic set of rules is very important in being able to name our organic compounds, okay? We can't go through and try to memorize everything because that's super boring, and we can't just be super vague about it because we're not actually going to be able to get the structure given the name, okay? So now, we're going to start on our systematic set of rules for naming organic compounds, okay? That hopefully will avoid all of these various little issues. Okay, so what is our nice systematic, methodical set of rules for naming organic compounds? So it is called the IUPAC system. This stands for the International Union of Pure and Applied Chemistry. Whenever I refer to this, I always say IUPAC. So it's an acronym, but I say IUPAC. That's what I'm saying. IUPAC, that's what I'm referring to. Okay, and so we also start our nomenclature topics by naming alkanes, because again, they're going to be the simplest and most basic of all of our organic molecules. So step number one in our systematic set of rules for naming alkanes or naming organic molecules is determining the parent chain of a molecule, okay? So for example, I want to name this thing, right? What is that thing? We don't know. We're going to figure out the name of it, okay? My first step in doing this is determining the parent chain, and the parent chain is defined as the longest chain, carbon-carbon chain. So longest chain of carbons and carbons, okay? So again, this doesn't have to be in any order that we have drawn it in. We're just looking for the longest consecutive carbon chain. So let's say I started going through this, and I said, okay, I've got 1, 2, 3, 4, 5, 6 carbons. So that chain gives me 6. There are other little branches off here, though. I could say, okay, I've got 1, 2, 3, 4, 5, 6, 7. So that chain gave me 7. I could also say, okay, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So is there any other chain in here that's going to give me something larger than 9? No. So I could try to find it. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. But I'm not going to find anything greater than 9. Okay? So that's step number 1. You have to find that longest chain. For this guy, that ends up being a carbon chain that has 9 carbons in length. okay? So we would go ahead at this point, and we would identify that chain. I like to circle things just to make it easier. Step number 1, find the parent chain. That's going to be the longest consecutive carbon-carbon chain. Step number 2, we're going to name that parent chain, okay? So the name of this parent chain is going to depend on the number of carbons that it contains in length. So right now, our parent chain has 9 carbons, okay? How do I know what 9 carbons is? Unfortunately, this is the one thing that you do have to memorize, okay? So I've given you guys a table that gives you the parent name for all of these things depending on how many carbon atoms it contains. So we go down here, we'll find 9 here. So the base of this is non. So for 9, our base is non, but because it's an alkane, what are we going to end it in? 8, right? So this is non, and then ANE. So note, we have a lot of these guys. I would recommend memorizing 1 through 10, right? So 1 carbon is meth, 2 carbon is F, 3 is prop, 4 is but, 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is non, and then 10 is dec. Okay? You need to memorize the first 10. I don't care, I won't ever put anything like 11 through 100, but you should memorize the first 10. And it gets pretty easy once you go through the meth, S, prop, but, pent, hex, hept. Okay. So with that, I want you guys. Oh no, forgot. Sorry, not yet. Okay, so there's a couple other little rules that go into it, okay? So let's say that we had a compound where there were 2 possible paths for our parent chain, right? So for example, in this compound we have 1, 2, 3, 4, 5, 6, 7. But another possible path was this, 1, 2, 3, 4, 5, 6, 7. This is the exact same compound. There are 2 possible parent chains. How do we know which one is correct? Our first one contained 7 carbon atoms. Our second one also contained 7 carbon atoms. So now, who's going to break that tie? Okay. So note that off of our parent chain, we have these other little branching groups. Okay. These things are called substituents. So substituents. On our guy on the left, we have 1, 2, 3 branches. We have 3 different substituents. So this guy has 3 subs. Whereas our guy on the right only has 2 branches. So we have 1 thing coming off, we have another thing coming off. So we only have 2 substituents on this side. So the tiebreaker is always going to go to the compound with the most substituents, right? Most branches off. So this guy had a parent chain that had 3 substituents that branched off of it. This guy had a parent chain that only had 2. This is going to be the correct parent chain. Correct parent chain. Okay, so we're always looking for the longest consecutive chain to determine our parent chain. If in the same compound there are 2 possible longest chains, then you're going to go with the one that has the most branches off of it, the most substituents. And I think the next one is an example. Okay. Yeah. Oh, one more thing. Sorry. Okay. I don't have this printed for myself, so this is the problem. Okay, so that's great, right? Parent chain, right? If there are 2 possible ones, we're going to go with the most substituents. What happens if we have something in a ring, right? Because a lot of times our parent chain will be in a ring. These do exist. They are possible. What are we going to do to name them as a parent? So it's going to be the exact same thing. We're going to count the number of carbons, right? So for this guy, we've got 1, 2, 3. What was our base for 3? We had meth, F, tri. This is, yeah. I know. You'll come back to try. So it's prop. I shouldn't expect you guys to know that at this point. So 3 carbons is prop, okay? Again, we're going to end it with ane. But to now signify the fact that it's a ring, we're also going to add on the prefix cyclo. So cyclopropane. This guy here, 1, 2, 3, 4, is butane. but because it's a ring, we call it cyclo. And then this guy is 1, 2, 3, 4, 5. That's pentane. But because it's a ring, again, we specify that by calling it cyclo. Okay, and those were all of the rules for all the parents. So these are the exact same thing, but all you have to do is add on that cyclo prefix. Okay, so now I want you guys to identify and name the parent chains in the following molecules. Unfortunately, this is it. This is just bad. Okay, so parent chains, I'm going to start from the top. We're looking for the longest string of carbons, right? So on the first one, I'm going to start over here to the left. We've got 1 carbon here. We can go 2 carbons. If we go up to the top, that's going to end real quick, so we're not going to do that. Then we've got 3. We go 4, 5. Now we have a branch here. If we go down this way, 6, 7, that'll give us 7. But if we went over here, we'll have 1, 2, 3, 4, 5, 6, 7, 8, right? So 8 is going to be the longest. So we can get rid of these guys. So 8 is the number of carbons. Again, we're going to look up, or we're going to hopefully at this point in time have memorized that 8 is oct is the base, and then because this is our parent and it's an alkane, we end it in ane. So this is octane. Okay, then over here we've got 1, 2, 3, 4, 5, 6. Now we have 2 branches here. Regardless of which one we go down, we're going to get the same number, and they're not going to differ in any way. They're all going to be the same, right? So this, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. No, 8, pardon me. So this is our parent. It's got 8 carbons in it. 8, again, has a base of octane. Let's draw correctly. That's not my eraser. Octane. Okay, so then finally, we've got a ring here, and the ring has 1, 2, 3, 4, 5, 6, 7. So the ring itself is either going to be the parent, or it's going to be one of the chains off the ring. For the chain off the ring, we only have 1, 2, 3, 4. So because the ring has 7, that's going to be our parent chain. And so parent for 7 is heptane. And then because it's a ring, we have to include the prefix cyclo. So cycloheptane is this guy. And then these guys will just be, this will be a substituent, this and this will both be substituents. I have to go back and edit that. That's the parent. That's number 1. Find the parent, identify the parent, name the parent, okay? Number 2, we're actually going to talk about naming these little branches off the parent, these substituents, okay? So for example, let's say that we had this molecule here, and we're trying to name it. Again, our first step is figuring out the parent. So we go in and we say, okay, I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbons. That's the longest chain of consecutive carbons. So 10 was what? I remember. So decane. So that's step 1, okay? Now, what about these little branches off? How are we going to name them, okay? We're going to name them using that exact same base, depending on how many carbon atoms are in each one, except now we're not going to end it in ane, like we did for the parent. Instead, we're going to end it in il, so YL. Il, right? So, for example, if we go up here to this substituent, right, how many carbons are in this little branch off, this little substituent up top? We've got 1, 2. So we've got 1, 2. The base of 2 carbons is F. So F, but now we're going to end it in il, right? So YL, ethyl. Same thing down here. We've got a 1 carbon substituent, One carbon is meth. So this guy is called methyl. Or if you're British, methyl. It's true. I shouldn't publish this. People get mad at me. And then, so we got methyl. And we go over here. We've got a substituent that has 1, 2, 3. So 3 is prop. So this guy would be called propyl. So ethyl, methyl, propyl. Okay, so notice these guys are kind of easy, right? All of these little chains, they're just consecutive. They don't themselves have any branches off of them. What happens though if we get something that has a branch off of it? Okay, so for example, what if we had something, I'm going to go forward and then we'll come back to that. What if we had something that looked like this, okay? So we've got our parent chain down here, and then we've got this one substituent, right? This one substituent has 1, 2, 3, 4, 5 carbons, right? So if we went back to that chart and we said, oh, 5 carbons, what would we call this? Pentyl, right? But this is different than what pentyl really looks like. Pentyl is 1, 2, 3, 4. This is pentyl, right? It's consecutive carbons in a row, right? This and this are not the same. This guy's pentyl, so then how do we name this guy? This is what we would call a complex substituent, a complex branch, right? Because it itself has a branch off of it as well. So to go about naming this, we're going to go into this little branch here, and we're going to find the parent chain, just like we did for the original overall molecule, okay? So in this little branch, who is the parent?
The 4.
We've got a 1, 2, 3, or we've got a 1, 2, 3, 4, right? So the parent chain is 4. What is the base for 4? This is butyl. Now, we're going to go in and we're also going to number our little parent, okay? So I'm going to go through and I'm going to give 1 to the carbon that's directly attached to the parent. I'm then going to give this guy 2, 3, and 4, okay? Okay, so now we've got butyl. That's the base of the complex substituent. What would we call this that branches off of butyl? The thing at the top. So this has 1 carbon in it, so what do we call this? Methyl, okay? So what we have is a methyl at the 2 position, right? These numbers are what are called locants. They tell us where things are at specifically, okay? So to name this, we're going to combine them. We're going to first tell where our substituent is, right? So what position is it on? It's on the 2 position. So we'll name this 2 dash, what is it? It's a methyl. And then what is the parent of this substituent? Butyl. So this thing, as a complex substituent, has different parts to it. It has the parent, which is butyl. It has 1 other substituent off of it at the 2 position. So we indicate that via our 2-methylbutyl. Okay, so this thing, very complex. So as a substituent, this isn't an ethyl, it's not a propyl, it's not a pentyl, it's a 2-methylbutyl. And again, there are a lot of different steps that go into actually naming this, okay? Now, this whole numbering thing we're going to come back to because we have to do it with the parent chain as well. So hopefully it'll make a little bit more sense. But as a note, right now, anytime we separate a number from a letter, we always use a dash. Okay? So that's why I knew to put 2-methyl, because I was giving a number, the actual locant, and then I was going into a letter. So we always separate those two via a dash. Okay, so again, these are complex substituents. If it's just a nice chain of 5 carbons, it's called pentyl, right? If it's a nice chain of just 3 carbons, it's propyl. It's only when you start to get branches off of substituents that it starts to get a little bit icky, okay? And when we actually put this in the name, we would separate it via parentheses as well. That'll make more sense when we start to assemble things, okay? Now, there are a lot of these, right? And a lot of them are very common. We'll see them over and over and over again. So for this actual group, its real systematic name is 2-methylbutyl, right? But there are also common names that go along with a lot of these complex substituents that we are allowed to use when we're naming them. So this is another situation where it would be beneficial for you to memorize a lot of these, okay? So for example, if we have a 3-carbon substituent that branches, there's only one way for 3 carbons to branch, and that is this guy, this nice Y shape, right? This is called, and its little common name is called isopropyl, right? Why is it isopropyl? I don't know the iso part, but I know the propyl is because there are 1, 2, 3 carbons in it, okay? Again, the isopropyl is the common name. You're allowed to use it. You can name it isopropyl. Its real actual systematic name is, if we went in and said 1, 2, this would be a 1-methyl, and then 1, 2 is ethyl. Right? Again, the substituent off of the parent of the substituent is a methyl group at the 1 position, and the longest chain is an ethyl group. Okay? Now, there are a couple for 4 carbons for the butyl branches. So the first one is, I think, the one that we just dealt with. This is sec-butyl. Now we have dealt with a different one. So sec-butyl has a chain of 1, 2, 3, and then it has a methyl group right off the 1 carbon. So this would be 1-methylpropyl as a real name. Another one is another of these iso. So isobutyl, Y iso, forms a Y, right? But then how many carbons are in the entire chain? 4, right? So isobutyl is the Y with 4 carbons. And then finally, another of these complex substituents of the butyl group is tert-butyl, right? So tert-butyl has, again, 1, 2, 3, 4, but they're all branching off of that first carbon, okay? I tend to start to get some sort of like little figures in my mind with respect to these names. Like, so for example, isopropyl, I know is that Y. Isobutyl is the Y, but it's got 4 carbons as opposed to 3. Tert-butyl, what does this look like?
Chicken leg.
Chicken feet, right? So tert-butyl always looks like the chicken feet. Sec-butyl is the one that I never remember, so it must be the last one possible, right? So isopropyl, isobutyl, sec, and tert. And then finally, we do have 2 for the pentyl, so 5. Last class, we went over the first couple steps in naming things, right? And again, with this whole idea behind nomenclature or naming, we want to be able to provide a name for something, and from that, know its actual structure, right? So the whole purpose of this is that if we name something, we can draw it correctly, right? Or vice versa, if we give you a structure, you should be able to provide us with a name, okay? Okay, so there was our first rule in doing this, right, in naming organic molecules correctly. And what was that? What was our first thing that we were going to do?
Find the parent.
Right, the parent, right? We were always looking for the parent chain, and we were going to identify, and we're also going to name it, right? And so what was the parent chain? This was the longest string of consecutive carbons, so longest carbon-carbon chain, okay? So once we had identified the parent and what it was and how many carbons were in it, how do we go about naming it? Right, so there were a bunch of those bases, kind of those base parent names, and what did we have to end everything in regardless? Because we're dealing right now with alkanes, ane, right? So however many carbons our parent chain has, we would name it with meth, eth, prop, but, however many it was, and then we would end it in ane, okay? Okay, so then after the parent, what did we have to focus on? The substituents, right? So after the parent came the substituents, and these guys were the branches off the parent, okay? And again, depending on how many carbons each substituent had, we use that exact same meth, eth, prop, etc. But then what did we end the substituents in? Instead of ane, we used il, right? And so then I showed you a bunch of complex substituents, right? So our first bit of substituents were just things that were just these nice long branches, and we could name them nice and easily. I then talked about how to name complex substituents. So these are substituents with a substituent, right? But then I also showed you nice, easy to use common substituents, right? So what were a couple of those? So for example, let's say I had a substituent that looked like this. What is that called?
Iso.
Iso what though?
Oh.
So this is coming off of, let's say something like that. This is isopropyl. Again, iso for the Y. Why do we call it propyl?
Because it has 1, 2, 3.
1, 2, 3 carbons in it, okay? So that's isopropyl. Those are going to be a lot more helpful than trying to actually give this a real name, right? So for this guy, this complex substituent, again, it's a branch that has a branch off of it. How would we go about naming that with its actual systematic name as opposed to the common isopropyl? Right. So for this guy, we notice how many carbons, what is the longest carbon chain in this little substituent branch? We've got 1, 2, right? If we went the other way, it would still be 2. So we'll say that this is our longest chain here. And then how would I identify this? What is this branching off of it?
1, 2, 2.
It's just a 1 carbon group. What is a 1 carbon group called? This guy is called a methyl, right? And then how do I specify where that methyl is at?
Where it starts.
I'm going to start to number this, right? My first carbon coming off of our parent chain is going to be given the 1 position. This guy is going to be 2. So overall, the name for this complex substituent is 1-methyl ethyl, right? So it's the substituent off the substituent and then the parent of the substituent. Isopropyl and 1-methyl ethyl are the exact same thing. Which one is easier to use?
Iso.
Isopropyl, right? And you can. So I would suggest using these common names as opposed to trying to come up with the actual systematic name for these complex substituents, okay? Okay, so that's where we were at, and we're going to do a little example utilizing that. The one thing I didn't talk about is cyclo, right? So I did mention when we're trying to find the parent that if the parent is a ring, we're going to include that cyclo prefix, right? So for example, in this guy, we've got 1, 2, 3, 4, 5, 6 carbons in this ring. That is our parent for this guy. So because of that, 6 carbons is what? What is the base? Is hex, right? But because it's a ring, what do I need to include as a prefix? Cyclo. So this is cyclo, hex, and then as a parent, we'd end it with ane, right? So for this guy, this would be cyclohexane, and as a substituent, we'd have 1, 2, 3. So what is 3 carbons in a nice long chain called? Prop, right? So this would be a propyl substituent off our cyclohexane. That is true. The ring is always a parent unless it is actually smaller than the longest carbon chain, okay? So for example, as we move down here, how many carbons are in this ring? 3. And then on our parent, our real parent, how many carbons do we have? 4, okay? So for this guy, the ring isn't the parent. The chain of 4 carbons is our parent, okay? So for 4 carbons, we have meth, eth, prop. This would be butane. But then how do we name this ring as a substituent? That's one thing that I hadn't mentioned quite yet. So how many carbons are in this ring?
Total 7.
In the ring.
3.
3, right? So we would name this as a 3-carbon substituent. So that is prop. But we also have to specify that it is a ring. So how do you think we're going to do that? How do we do that with the parent? Cyclo, right? So this is cyclo, prop, and then because it's a substituent, it gets the ill at the end. So this is a cyclopropyl substituent off of our butane parent. Okay? Yes.
What if the parent and substituent had the same amount of carbons?
What if the parent and the substituent had the same amount of carbons?
They had that ring.
Then the ring, I think the
was-
ring takes precedent.
Yeah.
If it's like 6 and 6, then this would take precedent. But if it is the parent actually has more, or there's a chain that has more carbons as opposed to the ring, then that's going to be our parent and the ring is going to be a substituent. So consider the ring just by itself. We're not going to continue to count past the ring. The ring is itself either the parent or is itself either the substituent. if I can make sense of that. Okay, so that's where we're at, right? I'd introduce you guys to all the various substituents. I'd also shown you all of the complex ones and their common names. And so now I want us to do a problem where you're going to identify all the substituents in a couple of different molecules. We have, again, another iso. So iso indicates a Y, but now it's a Y with 5 carbons. And then the chicken feet for this one is called neopentyl. So we have a chicken feet or chicken leg at this point because it's got a joint as well. So neopentyl is the chicken leg. Again, so these are very, very, very common, right? Instead of having to go in and find their systematic name, 3-methylbutyl or 2,2-dimethylpropyl, we are allowed to use these common names. So I'm showing these for you to just get an idea, but you should be memorizing these. These as common names you should know, and you should know what the groups are. So neopentyl, we've got isopentyl. Iso is always that Y, depends on how many carbons. And then the secs are kind of weird. Isopropyl, sec-butyl, you should be familiar with these. Yes?
I'm just wondering, how does the number come in again? Or like, how do you find out the number?
So for substituents like this, it's always just the number or the carbon that is attached to the parent is 1, and then you're numbering the new parent until the end of it.
Oh, okay.
So for example, this is our parent chain here.
Yeah.
This guy's going to get 1, 2, 3, 4.
Yeah.
And then whatever the branch is off of that, we specify that via its position. So this would be 3-methylbutyl. Yeah.
Yeah, I was a little confused on that part. But,
Yeah.
Okay. So basically, like the number until it gets to a cross, whatever.
The number until, again, you're finding the longest chain, right? Even if I had gone down this and called this 4, this as a methyl group is still at the 3 position regardless of which branch I take.
Yeah.
So I'm starting at the carbon nearest the parent with 1, and I'm branching until I get to the end of the line, the longest chain.
Okay.
I'm numbering until I get to the end of the line. Okay, so we'll pick up here on Wednesday. Naming and finding substituents onto these parent chains. So yeah, I would become intimately aware with all of these common names. Makes life a lot easier in using them. Yeah. That was that. Okay, so it would be helpful maybe to consult the notes from the previous one that show you isopropyl, isopentyl, I think. Is that one? Yeah. Tert-butyl, sec-butyl. But for all these molecules, I want you to tell me to identify and name the substituents for each one. So go ahead, give that a shot. Okay, so we went over these in class again. For each one, the first thing before you can name the substituent is to identify the parent. So if we start at the top on the left, I'm going to start counting carbons here. So 1, 2, 3, 4, 5. And then if I go 6, 7, 8, that's going to give me an 8. Whereas if I go 1, 2, 3, 4, 5, and then 6, 7, 8, 9. So this chain of 9 carbons is actually going to be our parent. And we can go ahead and get rid of these guys, because that's going to be part of our substituent. All right, so let's go ahead and fill these guys in. Okay, so now the things that branch off the parent are our substituents. So for this one, we've got a 1 carbon group here, and then we've got a 1, 2, 3 carbon group here. All right, so these are nice. They're easy substituents. They're not complex. 1 carbon, the base of that is just meth. So for substituent, this is methyl, right? We always end it in the YL. And then for 1, 2, 3 carbons, the base for that is prop. And so we just end it in YL. So propyl and methyl. Okay, so next one, we've got a couple of different things here. So number 1, we've got a ring that has 1, 2, 3, 4 carbons. So this is a 4 carbon ring. But then we have a branch off that as 1, 2, 3, 4, 5, right? So this is one of those things of who wins. with respect to a ring. I had said earlier that, oh, rings are always apparent. They're always apparent as long as they don't have a branch off of them that is longer than them. But in this case, there's a 5-carbon chain, right, that comes off of the ring that is longer than the ring itself, or it has more carbons than the ring itself. So because of that, this 5-carbon chain is the parent. And then the ring group here is the substituent, right? Because again, the parent's got to be the longest consecutive carbon chain, but we cut that off whenever we move into a ring. Okay, so the parent is 5. Then we've got pentane, right? The base of 5 is pen. And then this guy, as a substituent, is a 4-carbon ring group. So 4-carbon or 4 base is butyl, or bute, right? Because it's a substituent, we end it in YL, but then also because it's a ring, we have to include the cyclo. So this is cyclobutyl as a substituent. Okay, so then moving down, we've got 1, 2, 3, 4, 5, 6. We've also got, let's see, 1, 2, 3, 4, 5, 6, 7. I think the 7 is the longest chain. So then this one thing up here, this guy is our substituent. It is a complex substituent, right? So we can't just name this methyl ethyl propyl. Hopefully you guys can recall what this is called. It looks like a chicken foot. So chicken foot is tert butyl. So that tert is hyphenated, or it has a dash of tert and then butyl. And why do we call it tert? I don't know why they call it tert. There's probably some history behind it. But why do we call it butyl? Because again, there is 1, 2, 3, 4 carbons in this complex substituent. If you wanted to try to name it using its systematic name, then you could, and we'll just go ahead and talk about that. So in that, we're going to go ahead and identify the longest chain of carbons. It's a 2-carbon chain. We're going to number it 1, 2, with the carbon closest to the parent getting the 1. And then we're going to identify the substituents off of it. So we have a 1 and a 2. So this is a methyl, and this is a methyl. Right, so now we have, as a complex substituent, a 1,1-dimethyl, and then the actual parent of the substituent, 1,2-dimethyl ethyl. Right, and so if we tried to identify this, we would also have to put it into the name in parentheses as well. So terbutyl is 1,1-dimethyl ethyl. Okay, so finally we get to this last guy, which has a lot of these complex substituents. The parent here is going to be the ring, which is 6 carbons. So we've got 1, 2, 3, 4, 5, 6. This is a cyclohexene, or cyclohexane ring. Then we've got a bunch of substituents coming off of it. So we've got 1, 2, 3, 4. That's a substituent complex. 1 substituent complex, and then substituent complex. So all these are complex substituents, and it's good to kind of get those in your mind to be able to identify them. Okay, so going through this one is again a 4-carbon, 1, 2, 3, 4 carbons. It's a butyl group. It's the one that I never remember, so it must be the sec-butyl. Sec-butyl as a complex substituent. This guy is 1, 2, 3, 4. So this is another butyl group. But I do remember this one because it looks like a Y, and I know that all the Y's have iso in front. So this is isobutyl. So the next one, where are we at here? We're at this guy, right? So again, it's a Y, but there's only 3 carbons. So I know that any Y is iso with 3 carbons, though it's a propyl. And then finally we get to this guy. We've got 1, 2, 3, 4, 5. So it's one of those 5-carbon complex substituents. So this is a pentyl. It's a pentyl of something. And then again, this looks like a chicken leg to me. So we have like a little knee joint. And so the thing that looks like tert, but it's pentyl, is just neopentyl. And again, that's just how I memorize them, right? It doesn't mean anything about their like origin or anything, so don't take that for whatever it is worth, okay? Neopentyl. Begin assembling the entire name, right? So identify the parent, name the parent, identify the substituent, name the substituent. Now what comes next, okay? So the next step is we're going to go back to the parent and we're going to number the parent, okay? And so the whole idea about numbering this is we're essentially trying to provide a number or a location for all of our substituents, right? So that we can accurately locate where they're supposed to be at. So these numbers are what we call locants, okay? And so we're going to go back and we're actually going to number the parent chain. We're going to define a locant for each position, okay? So for example, in this molecule, we have a parent chain of 5 carbons here. So this is pentane. We have a methyl group that branches here. So we're going to go through and just number this 1, 2, 3, 4, 5. So we have a methyl at the 2 position. That's what we're essentially defining, okay? Now, one question may be, how did I know to start numbering it at this carbon? Right? Why didn't I start numbering it at this carbon? Why didn't I say, okay, we're going to name this 1, 2, 3, 4, 5? That depends on where the methyl group is at. Right now the methyl group is at the 4 position. Okay? So there are rules on how we actually define these numbers, these locants. And so the first rule in doing that if you have one substituent, you want to give that one substituent the lowest number possible. So you want to number the parent chain so that your first substituent has the lowest number possible. In this example, we have our first substituent here, right? So if I start numbering it 1, 2, 3, that's going to give my first substituent the 2 position. On the other hand, if I had started over here, 1, 2, 3, 4, 5, this would give my substituent the 6th position. Okay, we don't want to do that. This is incorrect. We want to give it the lowest number possible. Okay, that's if we have one. If we have more than one substituent, okay, we still want to give the first substituent the lowest number possible. So we want to number it so that the first substituent gets the lowest number. Right, so for example, here we have a substituent here, and then we have 2 other methyl groups here. So I have 2 options. I can start numbering this here at 1, 2, or I can start numbering over here at 1, 2. If I start this way, my first substituent gets what number? 2, right? If I start numbering it this way, my first substituent gets what number? 3. This guy trumps this guy because we want that first substituent to have the lowest number possible. So we would start numbering it at this position. This would be incorrect. Okay? Okay, so if there's only one, it's easy. We're going to give it the lowest number possible. If there's more than one, we're going to give the first substituent the lowest number possible. That's how we're going to number the overall chain. Okay, so now what happens if there's a tie in the first position? Right, so let's say that we have a chain where we have 2 options here. Right, we've got a substituent here, a substituent here. So if we started numbering it 1, 2 versus 1, 2, both of those would get the 2 position, right? So we have a tie in this situation depending on where we start numbering it. At that point in time, we're going to move to the second substituent, right? And we're going to number it so that the second substituent gets the lowest number possible. So the point of difference here, our second substituent comes at the 3 position versus our second substituent coming at the 5 position, okay? So this is not correct. This is correct because, again, we want to give the second substituent the lowest number possible. If you have to continue on, right, you want to give the third substituent the lowest number possible if you keep ending up with these ties. And at the very end of the day, if neither of those break the tie and you still don't figure out how to actually number the parent chain, you're going to give the substituent with the lowest alphabetical organization the lowest number possible. Okay, so I'll try to illustrate what I mean by that in this example. So in this guy, we have a bromine substituent and we have a chlorine substituent. If I started numbering here, I would have a substituent at 1 and I would have a substituent at 5, right? If I started numbering here, I would have a substituent at 1 and 5. So none of my rules thus far break the tie on who actually I'm going to number 1 versus 5. At this point in time, we want to give the lowest number to the lowest alphabetical organization, right? So bromine versus chlorine, who comes first in the alphabet? B, bromine, right? So bromine will get the 1 because it comes earlier on in the alphabet. You're going to alphabetize them. That's how you're going to figure out who actually gets the number, okay, or how we're going to organize the numbers. Okay, so again, the purpose of this is just figuring out how to number the parent, which is sometimes a little bit more difficult than we make it out to be. All right, what happens if we have a ring? So if we have a ring, something like our cyclohexane over here, what's great about rings is that we get to number them wherever we want to, right? So if we have a substituent, we're automatically going to give that the 1 position. But again, all of our rules are going to follow, right? So we want to give our first substituent the 1. Therefore, our second substituent, we also want to have the lowest number possible as well. Okay? So same rules, except you get to start numbering wherever you want to in a ring. You don't have to actually start at the first carbon. All right, so now, once we have numbered our parent, we are ready to begin assembling the full name. Okay? So there's a couple of different parts to this. We're going to start with the cycloalkane, with the cyclohexane, and we're going to assemble the full name for it. Okay? All right, so first step, we're going to identify the parent. All right, we have 1, 2, 3, 4, 5, 6. So our parent here is a 6-carbon ring. We're going to name it cyclohexane. Second, we're going to identify the substituents off of it, right? So how many different substituents do I have off of this ring?
2.
So I have a methyl group here, right? I have a methyl group here, and I have a methyl group here, okay? So how many different methyl groups do I have off of this ring? 3, okay? So we have a methyl, we have a methyl, we have a methyl. We're then going to begin numbering our parent, right? And so again, we get to start wherever we want with respect to this ring, but I want to give my substituents the lowest number possible. If I start here at 1, 2, 3, then both of these methyls get the 1 position, as opposed to starting here, 1, 2, 3. I'd have this at the 1, but these would both be at the 3. So this is the correct numbering, okay? Now, how do I assemble everything? So the first thing we have to show or tell is where our substituents are. And we're going to do that via our locants, okay? So right now, how many methyls do I have? I have 3, right? And where are they at? They're at the 1, they're at the 1, and they're at the 3 position, okay? So I'm going to specify that 1, 1, 3, because it's all going to the same methyl substituent. But then how many do I have again? How many methyl substituents do I have? 3. So now we have to specify that using a prefix, that we have 3 methyl groups, right? So this is when those old di, tri, tetra, penta prefixes come in. What is the prefix for 3? Tri. So we have tri-methyl. So substituents come first. Once we have named all the substituents, then we're ready to name the parent, okay? So this is 1,1,3 trimethyl. And then we just move directly into the parent. So this is cyclohexane, okay? Now one thing to note, anytime we have a number, a locant being separated from another number, we use commas, okay? Anytime we have a number separated from a letter, that's when we use the dash. Okay, so there's a dash that goes in there. When we have a number separated from a letter, we're going to use that dash to define that. So the name for this is 1,1,3-trimethyl cyclohexane. And there is no space between our last substituent and our parent chain. So these are our subs, and this is our parent. Okay, so we're going to do this again as an example, and then I'm going to have you guys do a few on your own. So this was easy, in theory, because all of our substituents were the exact same thing, but there is one more little thing that we're going to have to throw in if they are not, and that's how we organize our substituents. So let's go about naming this guy using our 4 various rules that we've just learned. So first step in identifying or naming the overall molecule is identifying the parent chain. So for this guy, if I look, I've got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. That's not going to work. 1, 2, 3. So I think that the parent chain here is this guy. So now, how many substituents do I have coming off of it? I have one group up here. Let me get my highlighter. I've got one group right here, and then I've got a 2-carbon group right here. Okay? So what are the 1-carbon groups called as substituents? This is a methyl. This is a methyl. And then if I have a 2-carbon group, what is this called? This is ethyl. Okay, so I've identified the substituents. The parent had 8 carbons. So what was that called? 8 carbons is octane. So now we're ready to begin numbering the parent, right, to define the locants. So note, if I start over here and I give this the 1, when does my first substituent come? What number?
5.
So 1, 2, 3, 4, 5. That's not great, right? If I start over here, 1, when does my first substituent get numbered? 2. So that's the first point of difference, right? That's going to define that I start here because I give my first substituent the 2 position versus giving it the 5, okay? So this is 1, 2, 3, 4, 5, 6, 7, 8. So now we are ready to start assembling everything, okay? The last example, we had 3 methyls, right? Now we have 2 methyls and an ethyl, okay? So when we have different type of substituents, we're going to arrange them alphabetically. Who comes first, E or M? E, right? So we're going to say the ethyl portion first. So number 1, where is ethyl at on our parent chain? It's at the 4 position, so that's going to start. So we have 4. We're separating a number from a letter, so 4-ethyl. Now we're ready for the methyls, right? How many do we have? There are 2. Where are they at? They're at the 2 and 3 position. So letter from a number, we always use a dash. When we have 2 numbers, we just separate it via column. So 2, 3, and then what is the prefix for 2? Di. So this is 2,3-dimethyl. And then those are all of our substituents. Now we're ready just to move into the parent, octane. 4-ethyl, 2,3-dimethyl, octane. So yes.
Why did you put a dash after ethyl?
Because anytime I separate a number from a letter, I use a dash. We had a letter moving into a number, so we always separate it via dash.
Okay.
When we have 2 numbers, we just separate it via commas.
And never between the 2 methyls?
Never between, no. Once we're at the last substituent, it moves directly into the parent. So there's no space, there's no dash there. Okay, so it's a lot, right? We're going to practice a couple of these. I want to make note though, right? For the methyl, even though we have this di in front of it, how do we alphabetize it? We've alphabetized it via the M, right? Because it's a methyl, even though there's a D in front with the di. So all of these prefixes we don't use in the alphabetizing, right? So di, tri, tetra, we don't use those as prefixes when we alphabetize. We just use the methyl, right? We also will not use the sec or the tert to alphabetize. These guys, if you note when you go back, all have dashes following them. The only ones that we will alphabetize as that letter is anything with an iso or anything with a cyclo. So again, I'm talking about substituents and how we actually alphabetize these things. If it has an iso, you're going to alphabetize it via the I. If it has a cyclo, you're going to alphabetize it via the C. But if it has a sec or a tert, or any of these other di, tri, tetra, you're not going to use those to alphabetize the substituent. So iso, yes. Cyclo, yes. Tert, no. For alphabetizing them.
Just second term?
Sec, tert, anything, yeah, so the iso, I think that's the only ones, are neo. Anything that has a dash after it, you're not supposed to use to alphabetize. If it doesn't have a dash after it, then you are supposed to. I'm gonna get angry comments. Nobody watches these videos, but I'm sure I'm gonna get some organic chemist in, I don't know, somewhere in Europe telling me, that's not true. You're lying to them.
In Europe.
Okay.
Watching this right now.
They are watching it right now. It's being broadcast live. YouTube live. Yeah. Okay, so let's try some, right? Because the only way to actually get used to this is actually doing it. So I've got a couple of examples, and then we'll go over them. We have a couple more examples, and then we'll move on.
Oh.
Okay, so we went over these in class. I'm going to go ahead and do them, provide the answers for these, and then the ones on the next page. If we're going to give the systematic name, a lot of times I'll ask also for the IUPAC name, right? So these guys are kind of synonymous with respect to one another. The first step in doing so is identifying the parent chain, right? So this is going to be the longest chain of consecutive carbons. For our first molecule over here, we've got a 1, 2, 3, 4, 5, 6, 7, 8. So this guy is our parent chain. It is 8 carbons, so 8 carbons is octane. So once we identify the parent chain, we're then going to move on to the substituents, right? So off of our little octane, we've got 1, 2, 3. All right, so all of these guys are 1 carbon substituents. So all of these guys are methyl groups. So we've got methyl, methyl, and methyl. And so then after we've identified and named the substituents, we're going to assign a locant to our parent chain. So we're going to number our parent. And again, we want to do so in a fashion that's going to minimize the numbers that our substituent gets, right? So there's going to be 2 possible ways that we can do this. We're going to start here. We're going to 1, 2, 3, 4, 5, 6, 7, 8. We could have also started at the other side and went 1, 2, 3, 4, 5, 6, 7, 8. Okay? So again, those are our 2 options. If we started with the black colors, so starting up here, then our first substituent would be a 3 position. So we'd have a 3, and then our second substituent would be at the 5 position. So this would be 5 and then 6. If we went with the blue colors instead, we have our first substituent again at the 3 position, but now our second one is at the 4, right? So our second one is at the 4, then our third one is at the 6. So because there's a tie in the first substituent, we'll move on to the second one. And a 4 is going to be a lower number than a 5, so this would be the correct way to number this, right? So we're going to go with the blue for our numbering, because again, it's going to be first point of difference. We want to give our second substituent the lowest number possible, and that comes when we start numbering down here. Okay, so once we have numbered it correctly, then we're going to symbol everything alphabetically. So right now, all we have are methyl groups, right? So we don't have to worry about alphabetizing. All we need to start with now are the locants. So this is 3, oops. So this is 3, 4, 6, and then there are 3 methyl groups. So we'll use the prefix tri. So we're going to separate that, a number from a letter via a dash. So then tri, and then methyl. And then those are our substituents. Now we're just going to follow with the parent. So trimethyl octane. Okay, so lots of little bits there. Oops. And let's highlight. 346 trimethyl octane. Okay, now let's move over to this guy. We'll start trying to find the parent. So we've got 1, 2, 3, 4, 5, 6, 7, 8. There's no other chain that's going to give us more than 8 carbons in this. So again, we have 8, which is octane. So now we're going to identify the substituents. So for this, we've got a methyl, we've got a methyl, we've got an ethyl, and then we've also got this thing up here, right? So we can go ahead and say a methyl, an ethyl, 2 carbons, and now this is a substituent. It is a 6-membered ring, right? So 6 is hex. It's a ring, so we need to specify the fact that it's a ring with cyclo, right? But now it's cyclohexyl because it is a substituent off of our 8-carbon octane parent. Okay, so now we have identified our substituents. We're going to go ahead and number our parent. So if we started numbering here on the first carbon over here, we'd have 1, 2, 3. Our first substituent would come at the 3 position. Whereas if we started numbering over here, we would have 1, 2, right? So our first substituent would come at the 2 position. So because of that, this guy is going to be the best way to number because we want to give our first substituent the lowest number possible. This is 1, 2, 3, 4, 5, 6, 7, 8. And we'll go ahead and erase these little guys, these little guys, and these little guys. Okay, so now we've numbered, we're ready to start assembling, and we're going to assemble everything alphabetically, right? So I had said that any type of prefix like di, tri, tetra, we don't use that in alphabetizing. We don't use sec, we don't use tert, but we do use iso to alphabetize, and we do use cyclo. So we have a cyclo here. C is going to come before M or E in the alphabet, so that cyclohexyl group will come first. We need to specify where it's at, so it's at the 2 position, 2-cyclohexyl, right? Now we'll move on to the next substituent in alphabetical order. That'll be the ethyl group. It comes at the 4 position. So now I have a letter, and I want to separate it from a number, which is the locant for ethyl. So I use a dash, and then another dash, because again I have a number from a letter, so for ethyl. And then we have the last one in alphabetical order, the 2 methyl groups. So we have a 5, 6. Oops. And let me scroll out here. So we have 5, 6. And again, anytime we separate numbers from numbers, we use a comma. And then dash. And because we have 2 methyls, we use dimethyl to specify that. So those are the last of our substituents. Now we're ready for our parent. And so we're just going to move directly into the parent. So this is 5,6-dimethyl, and then we just move into octane. Okay, so lots of little pieces, but again, follow the rules. So first off, identify the parent. Second, substituents. 3, follow the rules to number the parent correctly. And then 4, you assemble everything alphabetically. Assemble, right? And there are some rules with respect to that, but again, if you follow the letter from a number, separated via a dash, and every time a number from a number, separated via comma, everything should be good. Okay, so I would give these guys a chance too, so go ahead and give them a try. Try to provide the correct IUPAC, or correct systematic name for both of these molecules. You can push stop and then come back and I will answer with their names. Okay, so these are a little bit more challenging. So I'm going to start with this guy over here. We're going to follow the same rules. Our first step is numbering or identifying the parent chain. And so if we start over here to the left, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and then either of these two will be 10. So I think that's the longest chain in this molecule. I don't think you're going to find anything longer. So 10 for a parent, 10 carbons is decane. So now we'll go through and we will find the substituents. So we've got this substituent, oops, I want a highlighter, whatever this is, right? We've got this substituent, right? And then we've got this substituent, okay? So now we're getting into more of these complex substituents. The 1 carbon substituent right here, this is just a nice methyl group. Then we have a 2 carbon substituent here. This is a nice ethyl group, right? As we go up, ethyl with an E. As we go up to this guy though, notice we have 1, 2, 3, 4 carbons, right? This is one of our complex substituents. It's not just a 4 carbon chain. It isn't an iso group, right? Because it doesn't have a Y. It's not a tert group because it doesn't have a chicken leg. And so this is that oddball. This is the sec-butyl group. Okay, so again, those are things that you should have committed to memory, right? The fact that this is a sec-butyl group and that you can identify that. Worst case scenario, you could also try to name it via the systematic name, which I'm not going to go into, but if you have questions on that, please let me know. Okay, so now we have our substituents identified. We're now going to number the chain. If I started over here at 1, then it would be 1, 2, 3, 4, 5, 6. 6 before we got to our first substituent, whereas if I started over here at 1, we would get to our first substituent at 2, right? So that is going to trump starting on the other side. So we're going to go ahead and start to the left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now that we have numbered them, we're ready to start identifying or to start assembling everything alphabetically. So remember, with these complex ones, we're not going to use sec or tert when we alphabetize, but if we did have iso, we would use that, right? So because of that, sec is not going to be considered in the alphabetizing of this. We're going to start with the B, and B comes before E or M. So the sec-butyl is going to come first. So we have 5, sec, and then we also keep that hyphen, so sec-butyl. Spell, so butyl. So now we'll move on to the next one. So between ethyl and methyl, ethyl will come next. This is 4 ethyl. And then we have a 2 methyl. And then we have our parent, which is decane. So 5 sec-butyl, 4 ethyl, 2 methyl, decane. Okay, so now we're going to move over to this second one. So again, first step is determining the parent chain. So I'm going to go ahead and start off over here. So we have 1, 2, 3, 4, 5, 6, 7, 8. And then we have a couple of options here. We can go 9, 10, or we could alternatively go 9, 10, right? So right now we have a tie. And again, in the case of a tie with the parent, we always want to pick the parent with the most substituents. So if we look at the black dots as the parent, we're going to get 1, 2, 3, 4 substituents, pardon me. And then if we look at the red pathway as the parent, we would only get 1, 2, 3. Right, so maybe that's not the super clearest doing that. Let's go backwards. So I'm going to look at black first. Black dots are the parent. So if black dots are the parent, then overall we get 1, 2, 3, 4 substituents, right? Now if red is the parent, so we have red. If red is the parent, then we can go ahead and draw around our parent chain. Then all we get is 1, 2, 3 substituents, right? So even though it's a tie, red's only going to give us 3, whereas the black dots are going to give us 4. So we're going to go with the black dots as our parent, okay? And so I'll go ahead and erase these guys, the red. Okay, so we've got our parent chain. 10, again, is decane. So now we're going to go ahead and identify the substituents, right? So we've got 1 substituent here. We've got 1 substituent here, a substituent, and a substituent here. So this guy, our 1 carbon substituent, is a methyl group. This guy, our 1 carbon substituent, is another methyl group. Right, and then over here we've got 2 carbons, so this is an ethyl. There's no branching in that substituent. And then here we've got 1, 2, 3 carbons in a Y shape. So remember, this is a complex substituent. There is a branch. This is called the isopropyl group. So isopropyl. Okay, so now after we've identified the substituents, we are going to number the parent chain. And we're going to do so that our first substituent gets the lowest number possible. So if we start over here, 1, 2, 3, 4, 5, our first substituent is at the 5 position, whereas if we start over here on the right, we have 1, 2, our first substituent is at the 2 position. So that's going to be the better way to go here. So we can go ahead and erase these guys and go ahead and fill in the rest of them. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now once we have numbered the parent chain, we are ready to start assembling everything in alphabetical order, right? So right now we have 2 methyls, we have an ethyl, and an isopropyl. And remember, we do get to utilize the iso in our alphabetizing. So we alphabetize that as an I. So we'll start with ethyl because that comes first in the alphabet. So the ethyl group is at the 3 position. So this is 3 ethyl. And then we have the isopropyl. The isopropyl is at the 6th position. So 6 isopropyl. Make sure that's legible. Isopropyl. Then we've got a methyl and a methyl, and this is at 2,4. So 2,4 dimethyl. Again, we use the di because there are 2 of them. And so that's all of our substituents. Finally, we end it in our parent chain, so dimethyl decane. So 3 ethyl, 6 isopropyl, 2,4 dimethyl decane. Okay, so that is naming in a nutshell. So I'm going to do this one in class, but I'm going to go ahead and finish this presentation so I can post it. So the kind of the reverse of everything that we've been talking about, thus far we've given you a structure, right? And we've said, okay, provide the name for it. And that's what we've been doing. So in this little part, we're going to kind of go in reverse. We're going to give you the name, and you're supposed to be able to draw the structure from it. Okay, so I'm going to talk about how you can go about doing that, and then there'll be a couple of example problems. Okay, so for example, in this problem, they give you the IUPAC name, and they want you to draw the structure, right? And so the IUPAC name is 3-isopropyl 2,4 dimethylpentane. Okay, so whenever I start these types of problems, I always start with the parent. So pentane. Pentane is 5 carbons in length. And so I'll go ahead and draw in my bond line structure a 5 carbon chain. So we've got 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Right? And so then, because I'm kind of given some freedom here, I can start numbering at either side, right? So I'm going to go ahead and start numbering 1, 2, 3, 4, 5. And now I'm just going to put the things that they tell me are specifically there at the position that they're at. So for example, they have a methyl group in the 2 and the 4 position. So all I'm going to do is just draw a line in the 2 and the 4 position. We'll make that look a little bit prettier. So get rid of the number here, clean up that. So this is our 4 position. And then at the 3 position, there's an isopropyl group. So again, this obviously draws on your ability to identify what an isopropyl group is. I know that isopropyl is the Y, right? This is our parent that it's coming off of. And the difference between isopropyl and let's say isobutyl is this only has 1, 2, 3. So it's propyl, right? And prop is the base for the 3 carbons. Okay, so this specifically is at the 3 position. So we'll go ahead and add that on. So we've got a nice Y at the 3. Right? And so now if you wanted to keep these guys, you could, or you could also get rid of them to make it nice and pretty, just to show the overall structure, right? Regardless of how we had started that, if I had started numbering over here, I would get the same complex or the same compound. It may look slightly different, but it still is the same, right? It's gonna rotate essentially and be able to find the exact same complex. Okay, so that's one example. So, and then we've got a couple more examples here. So ideally you guys should take some time if you're listening to this and try to draw these and then come back for the answer. And I will provide the answers for both of these after a break. Okay, so again, we're given the name here and we're trying to draw the structure. So for the first one, we have 4-ethyl 2-methylhexane. So I'm going to start again with the parent. The parent here is hexane. So using bond line structure, I'm just going to draw a 6-carbon chain. So as a note, 5 carbons is always 2 mountains. And so then 6 carbons is just going to be that extra peak, I guess, or something like that. So we have 1, 2, 3, 4, 5, 6. So now I'm going to start numbering. I'll start numbering on the left. So this is 1, 2, 3, 4, 5, 6. There's a methyl group at the 2 position. So I'm just going to go and draw that. And then at the 4 position, there is an ethyl group. And so that's what that looks like. So this is 4-ethyl 2-methylhexane. And then finally we have a long name. We've got 1,1,2,2 tetramethyl cyclopropane. First thing I'm going to do is draw the parent. So cyclopropane is a 3-carbon cyclized ring. So propane again is 3 carbons. Cyclo tells us it's a ring. For this one I can start numbering wherever I want to, and maybe I'm going to draw a bigger ring. That's not going to be helpful. So we get this nice triangle, right? And I'm going to go ahead and zoom in here. So let's say I start numbering 1 at the top. So this is 1, 2, 3. So for here we have 2 methyls at the 1 position. So this is 2 methyls at the 1 position. And then I have 2 methyls at the 2 position as well. And so here's 2 methyls at the 2 position. So it's weird looking, but this is 1,1,2,2 tetramethyl cyclopropane. Okay, so hopefully you guys could do this. It all hinges on your ability to know what an isopropyl group is, know what an ethyl group is, and be able to draw those at command without having to utilize any type of reference information.